Stars are in binaries. A large fraction of them interact. In fact, a large fraction are triples and quads. And this is, from the point of view of supernova, is other than just playing games with stripping mass, no one really does anything like that. Okay, so suppose we actually want to go to Adam and say, well, okay, here's the answer you should get, right? If I give you a 15 solar mass star, you should get this. If I give you that, you should get that. How are you going to do this mapping between stars and outcomes? And what people have done for the last 20-odd years, mainly as the amount of archival Hubble data grew, is when a supernova goes off, you go back and look in the Hubble archives and try to find the star which exploded. This is tricky. You can only do it to a few tens of megaparsecs. The other problem is basically Hubble observes only in V and I. Okay? And so in most cases you get for the progenitor at most 1 or 2 filters. And so generally you do not have enough data to clearly measure things like temperature and extinction, just because you don't have enough data. And so the number of supernova progenitors with good data is still about 10. Okay. The ones which have been found are basically all the progenitors of type 2 plateau supernova, which are believed to be red supergiants with a still massive hydrogen envelope. There are claims and arguments about a few of the other cases, but the reasons is if you go to the supernova which come from stripped stars, it's essentially like finding the Wolf-Rayet stars, right? They're very, very luminous, but they're essentially optically invisible. And so they're very faint in the optical, and so it's hard to identify observationally the progenitors of a stripped supernova. We looked at this, 10 years ago and said, wait a minute, there seems to be a shortage of high-mass progenitors. Is that if you go up towards the upper red supergiants, they should be easy to find, and yet no one was finding the more massive red supergiants. And Stephen Smart and his group did this nicely a little bit later, and basically they are finding red supergiant progenitors from around 8 to 16 or 17 solar masses. Again, the error bars on any mass are 2, 3, 4 solar masses. They're not precision masses. And so there seemed to be a dearth of things around 20 or 25 solar masses that you expect to die as red supergiants, but no one was finding. And so Smart called this the red supergiant problem, and it hasn't gone away. So here's Smart's most recent version. Here is estimates of progenitor masses, just sorted. Okay, so you can sort of see the typical error bar on estimating a mass, and then something of just limits. And if you made this a saltpeter IMF from 8 to 30 solar masses, where you might still have red giants, you can see it's not tracking. Okay, and so if you say these higher mass red supergiants are not exploding as supernova, they would represent 10, 20, 30% of core collapses, depending on how you want to cut the pie. So how can you get out of this? So one is you take the stars and turn them into Wolf-Rayet stars. So basically, you take the stars which you thought were red supergiants around 20, 30 solar masses, you turn them into type 1b supernova, and so you don't find them as progenitors of type 2p's. You can use dust or something else to try to make a mess of the mass estimates. That doesn't really work. And you can play another game, which has been done by the Washington group mainly, is you can try to estimate the masses of progenitors from the surrounding stellar populations. And there, basically, you also find that basically the stellar populations you see don't contain enough young stars to correspond to 20 or 30 solar mass stars. And so you infer the mass distribution of progenitors from their local stellar populations that also seems to be missing these higher mass regiments. Oops, wrong direction. Okay, another interesting clue is something which some people in this room have worked on, is the mass function of compact remnants. So this is I can't remember exactly whose compilation is, but anyway, it may have been yours. But here's sort of distribution of neutron star masses and of black hole masses. And it's been sort of known for a long time that between the masses of neutron stars and the masses of black holes, there's either a gap or a minimum. And various people have very religious views as to whether it's a gap or a minimum. But let's just say it doesn't really look like a nice, smooth, continuous distribution. So the other thing is all of these black hole masses are basically below 10 solar masses, which is rather peculiar because most of these stars which are going to explode are more massive than 10 solar masses when they explode. And so this is what really drove this idea of trying to have fallback in supernova, that you had to have somehow take a 20 solar mass star at death. In the process of exploding it, you would eject 15 solar masses, and then that would let you leave with a 5 solar mass black hole. Except the explosion actually starts from the protoneutron star of around 1-ish solar masses. And so you have to somehow finely tune the explosion so you can get 4 solar masses to fall back. In modern simulations of explosions, basically fallback doesn't exist.
Chris, there are 3 that are about around 15.
Yeah, you can see one creeping down to the edge.
From LIGO we have many
No,
foreign.
but I mean,
Yeah, but like, the LIGO statistics, and the LIGO statistics are actually consistent with this. It's just the selection function for LIGO is so mass weighted that if you have one high mass merger, that's the way they're going to find. And so this is what drove this idea of needing fallback supernovas. It seemed the only way where you could explode starting with a protoneutron star but end up with something which was more massive. So Fryer doesn't come to this conclusion. Fryer comes to the opposite conclusion. But my read of Fryer's papers, if you look at the distributions they get from their fallback models, it just doesn't reproduce what you see. Neutron stars themselves want very, very little feedback. And as I said, in modern explosion theories, basically fallback doesn't exist. It's you either explode or you don't. So this is where, I guess, having a long memory of the literature models. So in 1980, a Russian named Nadezhin wrote a paper in which he pointed out that the envelopes of red supergiants are so weakly bound that the drop in the mass of the star due to the emission of neutrinos, which is 1/10 or 2/10 of a solar mass of energy, is enough to drive a weak shock into the envelope of the red giant. And so if you have a failed supernova of a red supergiant, the mass of the black hole you get is the mass of the helium core, and the hydrogen goes drifting away. Okay. And so they simulated this, and also Elliot Quatert's group has simulated it, and so Nadezhin just did a little analytic model. But you can actually simulate this. If you take a red supergiant, drop the mass by 1/10 or 2/10 of a solar mass, you get a weak shock because of the hydrogen envelope, and it gets ejected. And so this actually works out very nicely for producing the mass function of black holes, is if you say things with a high compactness turn into failed supernova and become black holes, but the mass of the black hole is the mass of the helium core because you eject the hydrogen, then you very naturally produce black holes in this 5 to 10 solar mass range that seems to dominate the black hole mass function. It just happens naturally, no fine tuning. Right? That's the masses of the helium cores of stars, which are 20 solar masses. And so you don't have to do any fine tuning about fallback, which doesn't seem to exist in any case. All right, so how are you going to find failed supernovae that exist? Cleanest would be, as said, gravitational waves or neutrinos, but that you can only basically do in the galaxy for the foreseeable future. And so if the rate in the galaxy is one supernova every 50 or 100 years, and failed supernova are 10, 20, 30%, it's going to be a really long thesis project. So what you have to do is you have to look at a sample which has a high enough supernova rate that you actually would have, say, a supernova every year. And you can do that by basically looking at all of the star-forming galaxies within about 10 megaparsecs. And so if you look at all the star-forming galaxies within 10 megaparsecs, and what you look for is instead of an explosion, you look for a star to go away. There may be some intermediate transit, right, but you don't have to have any view as to what transient is associated with a failed supernova. You have a very simple thing, is you start with a star and you end up without a star. Okay, so you just look for a vanishing.
Chris, just a clarification. You mentioned this unbinding of the hydrogen envelope. It doesn't produce any electromagnetic counterpart?
It does. I think that's the...
How easy is it to see it?
It's here, I'll come to it.
Okay.
So when we started this, there really wasn't much research into what failed supernova looked like, and you could sort of sketch out all sorts of diagrams. But now it's sort of pretty clear as this is what you would be looking for in a failed supernova. So this is the light curve you would get from ejecting the envelope. It's basically powered by the same things as a supernova. It's basically you're going to recombine the 10 solar masses of hydrogen, and you get the recombination energy, or however much of that you can radiate versus go into PdV expansion. And so you get a weak shock breakout, much weaker than you would get from a normal supernova because the shock velocities are order of magnitude lower. It's like 100 or 200 kilometer shock that's associated with the ejection. Then you get a transient, that's maybe a few million solar luminosities. It'll be somewhat cooler than a normal supernova. And then somewhere back here probably would form dust and fade out. You can see the time scale is quite long because the ejection velocities are low compared to a supernova. And in supernova surveys, right, these are hard to find. Okay? It's a little bit too faint for the amount of volume you can survey. ZTF has a reasonable chance of trying to find some of these. Although it's been interesting, is my ex-student Adams has had trouble convincing them that it was worth trying to look for. I think they finally are going to do it. Anyway, so that's the sort of signature. It's a million solar luminosities or so, lasting a year or so. Okay, so you have to find individual stars in galaxies which are megaparsec away. And so whereas with Assassin, we can find a supernova every day using a 14-centimeter aperture, that's not going to work for this. And so we actually use is the Large Binocular Telescope and the prime focus cameras, which you can see here and here. And so actually, for the purposes of doing this project, it's actually the best telescope. Is the combination of aperture and field of view is sort of perfect. Other things have more field of view, but it's all wasted. So hypersuprime cam, basically, it has a higher entendu, but it's all stuff off the galaxy where there are no stars. And so, basically you can look at 27 nearby galaxies. They have a historical core collapse rate of 1 per year. And so that means you're looking for a failed supernova happening every 3 to 10 years. Okay? Again, it's not an instant gratification project. And what we do is on one camera on one side, we just observe at R band. Camera on the other side, we cycle through UBV. And then we try to monitor every galaxy several times a year, and then put each galaxy through a more intensive monitoring period to get the variables, which are sort of a source of pain. We do it all using difference imaging.